seen it, right? That sudden flash of lightning. Or maybe you felt that terrifying shake of an earthquake. These things are some of nature's most powerful forces. So, what's really going on behind the scenes? What's the science behind all that spectacle? Well, today we're going to break it all down.
So let's start with a basic question. What is a natural phenomenon? It's a good place to start. And really, it's pretty simple. It's any event that happens in nature without any help or interference from us humans. We're talking about everything from the tiniest ripple in a pond all the way up to these massive, planet-shaping events we're diving into today. It's just nature doing its thing. And believe me, the list of these things is, well, it's long and it is powerful. You've got volcanic eruptions, cyclones, massive floods, landslides, tsunamis, huge forest fires, you name it. These are the events that are constantly shaping our planet. Now here's the thing, we can't stop them, right? But what we can do is understand them. And that's why today we're going to zero in on two of the most common and, frankly, awe-inspiring ones, lightning and earthquakes.
Okay, first up, lightning. That brilliant and, let's be honest, sometimes terrifying flash in the sky. It's way more than just a bright light, you know? It's actually a massive electrical discharge. And the crazy thing is, it all starts with something you've probably played around with yourself, just on a much, much smaller scale.
Yep, it all boils down to static charges. You know exactly what I'm talking about. Remember being a kid and rubbing a balloon on your hair to make it stick to the wall? That's it. That's static electricity. It's just an imbalance of electric charges that build up on a surface. Now, just imagine that instead of a balloon, the balloon is a gigantic, swirling thundercloud. And the rule for how these charges work is super, super simple. Opposites attract, and charges that are the same, well, they repel. They push each other away. Think of it just like magnets, you know? A positive and a negative charge, they want to get together. But two positives or two negatives, they want nothing to do with each other. This really basic push and pull is the engine driving every single lightning strike.
So, you might be wondering, how in the world does a cloud build up that much charge? Well, it all starts with total chaos inside the cloud. You've got this wild mix of air currents shooting up and water droplets falling down. All that rubbing and bumping, that friction, it separates the charges. The lighter positive charges get pushed up to the top of the cloud, and the heavier negative ones sink down to the bottom. So now you've got this massive negative charge at the cloud's base. And what does it do? It starts attracting positive charges from the ground below it. Eventually, that electrical tension just gets to be too much. It has to go somewhere. And bam! That brilliant spark we see as lightning, that's just nature finding a way to release all that pent-up energy.
Okay, so that's the science, which is pretty cool, right? But so what? Why does this actually matter to you and me? Well, here's why. If you understand that lightning is basically just electricity looking for the fastest, easiest path to the ground, you can take steps to make sure that path isn't, you. So let's get practical and talk about how to stay safe. Right, so if you're inside when a storm hits, you're already in the best possible place. But that doesn't mean you're totally in the clear. The number one rule is to avoid anything that can conduct electricity. So that means no showers, no washing dishes, because those metal pipes are like a superhighway for electricity. You'll also want to unplug your expensive stuff, like your TV, your computer, to protect them from power surges. And yeah, stay off any old-school corded phones. Basically, you just want to disconnect yourself from anything that physically connects your house to the outside world until that storm rolls on by. And now, if you get caught outside, it's a whole different ballgame. The rules completely change. Remember, lightning is lazy. It wants the path of least resistance, and that usually means the tallest thing around. So your job is to not be the tallest thing. Get away from tall trees, get out of wide open fields, and please do not use an umbrella with a metal rod. You're basically holding up a lightning rod. If you're really stuck out in the open with nowhere to go, your best bet is to make yourself as small a target as you can. Squat down low to the ground, don't lie flat, but squat. Look, it's not going to be comfortable, but this isn't about comfort. This is about staying safe.
All right, let's shift gears. We've talked about the sky, now let's go deep underground. We're talking about earthquakes. Now these are a totally different kind of natural event, but just like with lightning, there's real, understandable science behind them. So what is an earthquake? I mean, at its most basic level, it's exactly what it sounds like. The earth suddenly starts shaking. But the important thing to know is that this shaking is not random. It's caused by a huge, sudden release of energy from deep within the Earth's crust. But why does that energy get released in the first place? Well, it's because the Earth's crust isn't one solid piece, like an eggshell. It's actually more like a giant cracked jigsaw puzzle. And those massive puzzle pieces are what we call tectonic plates. The thing is, they're always moving, just incredibly slowly. As they grind past each other or crash into one another, huge amounts of pressure build up along the edges. Then, at some point, they slip. And when they do, all that stored up energy is released in a single moment, sending shockwaves through the ground. And that is the shaking that we feel as an earthquake. And this is so important because it explains why earthquakes don't just happen anywhere on the planet. They're concentrated right along the boundaries where these giant plates meet. We call these areas seismic zones or fault zones. You can think of them as the weak spots in the Earth's crust. They're the front lines where all this geological action is taking place. And the power that gets unleashed in these zones, it can be absolutely devastating. We measure this power on what's called the Richter scale. The key thing to understand is that each whole number on that scale is 10 times more powerful than the one before it. So the jump from a 6 to a 7 is huge. Anything above a 7 is considered a major, major earthquake. To give you some perspective, the catastrophic earthquakes in Bhuj in 2001 and Kashmir in 2005 were both over 7.5 on that scale. We're not talking about a minor tremor here. This is a force that can literally reshape the land around you. So how on earth do we measure something so powerful? Well, we use this clever instrument called a seismograph. And honestly, its genius is in how simple it is. Imagine you have a really heavy weight hanging on a pendulum. When the ground starts to shake, the whole machine shakes with it. But that heavy weight, thanks to inertia, it wants to stay put. It stays pretty still. You attach a pen to that weight, put it over a rotating drum of paper, and voila! The pen draws a wiggly line that gives us a perfect visual record of the ground's movement, how strong it was, and how long it lasted. And here we are again, back to the main point. Just like with lightning, understanding the science behind earthquakes is our single best tool for survival. Look, we can't predict exactly when they're going to happen, but we can absolutely prepare for them, and we can know exactly what to do when one strikes. When it comes to earthquakes, preparation is everything, especially if you live in one of those seismic zones. It really starts with how we build things, designing buildings that can flex and sway instead of just cracking and breaking. But it also comes down to what you do inside your own home. You've got to secure heavy furniture like bookshelves and cupboards to the walls so they can't fall on you. And just be smart about what's hanging on the wall over your bed or your sofa. I know these sound like small things, but trust me, these simple steps can make a life or death difference. Okay, if there is one thing you remember about what to do during an earthquake, let it be these 3 words: drop, cover, and hold on. It's that simple. First, you drop to the ground before the earthquake throws you down. Then you take cover under something strong, like a sturdy table or desk. And finally, you hold onto that table leg until the shaking stops. See, it's usually not the shaking itself that's the biggest danger, it's stuff falling on you. This one simple action, drop, cover, and hold on, is your absolute best defense. Of course, what you do exactly depends a little bit on where you are. If you're inside, your goal is to get under that sturdy table. If the quake hits while you're in bed, hey, good news. Just stay there, roll over, cover your head with your pillow. Now, if you're outside, you do the opposite. You want to get into a wide open space, as far away from buildings, trees, and power lines as you can get, anything that could fall over. And what if you're in a car? A car is actually a pretty safe place to be. Just pull over to a safe, clear spot away from overpasses or power lines and stay inside until it's over. So, at the end of the day, we can't stop the lightning from flashing, and we can't stop the ground from shaking. That's just not in our power. But by understanding why these things happen, why charges build up in a cloud or why those tectonic plates are always shifting, we can replace that raw fear with real practical preparedness. Science doesn't give us control over nature, not at all. But what it does give us is the knowledge, the power to live more safely alongside it. And when you think about it, that really makes all the difference, doesn't it?